Hello everyone, and thank you for joining me today. My name is Matt Bemis, and today I'm going to be looking at predicting pressure drop through a valve using the SimScale platform. First, just a couple notes about myself. I've been running simulations basically on a daily basis for about 4 years now. I've worked in a few different roles doing either technical support or CFD consulting basically. So I've worked with a few different CFD packages, worked for a few different companies, and have spent kind of my time in that area in learning everything I can about simulation in general. So just kind of an agenda and rules for today. This session will be recorded, and if you're having any sound issues, we do have a chat, so please just chat me via the GoToWebinar module there. Of course, the topic is going to be pressure drop through a valve. I'm going to go through a few slides, basically just on the platform and a little background in general, and then we'll jump into a case study that I did, and I'll spend some time in the platform and look at the results there. So first, in case there's any users that are unfamiliar with SimScale or really unfamiliar with simulation in general, I'd like to just touch on a few topics there. So using simulation, and here we basically mean modeling either fluid dynamics or solid mechanics, right? So usually referred to as CFD, computational fluid dynamics, or FEA. You get to basically predict the part, model, or system performance before building a physical prototype and testing it. So this allows for much faster design iterations in a design life cycle. You can virtually prototype and make changes and then test those changes and see what the outcomes are like at a much faster rate than physically testing. From a kind of a macroscopic point of view, this allows you to consider a wider range of solutions, and it really minimizes bad decisions, bad designs, and just reduces the chances of failure. So I would like to just give a bit of a brief introduction to the SimScale platform. So this is a 100% cloud-based CAE solution, and it's not only is it cloud-based, there isn't even a client. So you use the program by going to simscale.com in Google Chrome or whatever web browser you want, and just start working in the web, in the workbench. It's the first solution like this, which is awesome. It's extremely impressive technology, and I've learned to love it with my time here. Now, when we say, CAE or simulation, I'm specifically talking about this is a full-fledged CFD, FEA, heat transfer, and thermomechanical analysis solution. What I love about the fact that it's cloud-based is there's only one version of the software. You always have access to the latest builds of the software, and the pace of software development from our end, and the bug fixing QA is way better than a desktop application, which I used to use. So I'm a big fan of this solution. So with a subscription to SimScale, we don't price it based on features. So if it's just one number and you get the entire solution. So you get access to structural analysis, fluid flow analysis, thermal, all in one platform. We do have world-class support. There's actually live in-product chat, which I think is a first for the simulation field, basically. We, of course, have traditional phone and email support. Now, one of the biggest perks about this being browser-based is that you can actually, if you're having a trouble with your design or your simulation, you can actually just copy and paste the URL. You have to give us permission, of course. We can't see your projects unless you say we can. But all you have to do is just copy and paste the URL and drop it into the chat, and you're good to go. It's just an incredible capability that allows me, when I get it on my end, I can see, you set boundary conditions wrong, maybe try a different meshing strategy. something along those lines. It really speeds up the time to solution. There is a huge database of public projects that you can leverage to basically use as a template. So if you're doing some kind of external aerodynamics study, you've really never done that before, you're kind of curious how people what meshing strategy they might use or what turbulence model they might use, you can just go look up a public project that is available, that has good results, and then kind of mimic the approach that's taken over there. Again, with this platform, because it's cloud-based, collaboration between teammates is basically second to none here. So if you're working with coworkers in different geos, you don't have to remote desktop or use like TeamViewer or something to work on the same project. If you have a bit of experience in the the simulation field, you can't really easily move results between computers. The data's in the gigabytes of size, and it's just too painful. So being able to not have to move results, no matter where you go, you can just log in on a website and see your results is phenomenal. You also have instant access to a HPC environment. So you can choose when you go to hit run how many cores you want to run on. So we have, your standard 8, 16, but then we have 32, 64, or even 96 cores. Now this is our own hardware. It takes, there's no upfront cost on your end, and this is all on our end. So, a traditional simulation computer might have 16 cores. So you're going to have, 6 times the computing power running on 96 cores. So nowadays, when I spend time simulating, actually the most time investment for me is either post-processing or setting it up. It's no longer, waiting for the solution to converge, because that happens so fast, which is pretty incredible. It's something that's new to me still. All right, so now to jump in today's topic, I'm going to be looking at pressure drop through a globe valve and calculating a flow coefficient for that valve. So here's the geometry I used. I got it off of GrabCAD. It's a standard globe valve, and flows going from left to right, and there's labeled some of the different components. Really what we care about here is the plug and the body, or the housing. The question we're trying to answer today is, for a given pressure drop, what is the resulting flow rate, and how does that change with respect to plug position? I'm also going to take a look at forces on the valve, on the plug, and how that changes with respect to plug position. So here's a cross-sectional view of the CAD. On the left is the original untouched geometry, and on the right is kind of, simulation-ready geometry. So I basically combined a bunch of bodies. Again, I was going to move that plug in, but I combined it with the stem and all. Really, as long as that part can move in the vertical, axis, basically, I'm good to go. I also filled a bunch of small holes, basically. You can see the threads and some other ugly features. So it didn't take a lot of work. That cleanup was very quick, and now we basically have a simulation-ready valve, and we can start to extract the fluid volume. So here's actually the fluid volume. So you actually want the negative of your geometry, which, if you've never done simulation or CFD specifically before, it's a little counterintuitive. So we don't really care about the housing. We just know it's a boundary, and fluid flow doesn't go through its metal wall, right? So if you look in the center there, it's actually completely void, and that's where the plug and the stem is. So I did the flow volume extraction in CAD, although we do have an option to now do it in the platform, so it's up to you. I added an inlet and outlet extension a bit. I added basically pipes on each side, and this is to just allow for fully developed flow. You need a certain amount of entrance length before the flow profile across the pipe is considered fully developed. And if you're going to benchmark against an experimental rig you have, the number one rule I always tell people is you want it to look just like your experimental. setup. So there are standards out there if you're just if you don't have an experimental test. But if you only have 2 diameters upstream and there's your pump and 3 diameters downstream, just model that. That's fine. It's better if you're going to try to correlate it. You need to stay close to what the experiment looks like. So what is the end goal of the simulation? So we're going to be calculating flow coefficient, which is a common industry value that's used to kind of evaluate valves. The flow coefficient is basically flow rate. This is in gallons per minute times the square root of specific gravity over delta P. Specific gravity for water is 1, and then the delta P is in PSI, and flow rates in GPM. So it just describes the relationship between pressure drop and a corresponding flow rate. Now, how this is usually set up is you fix the pressure delta and then look at flow rate. So usually the setup is that the pressure delta is 1 PSI. We're using water, so specific gravity is 1, and this actually just kind of reduces to it's a function of a flow rate. So this is kind of what we're after. Different valves perform differently as they start to open in terms of what percentage of flow starts to come through the system. Now, the valve lift going to 100% is just whatever the predetermined fully open position is. It's a little different than like a different kind of valve where 90 degrees is fully open. This is just, in my case, I'm saying, hey, 10 millimeters up is fully open, and that's that. Now, full flow, that just corresponds to what the flow rate is at that fully open position. So fully open for me is 10 millimeters, and go from there. All right, just taking a quick look at the setup. So like I said, the way to approach this is you define a 1 PSI pressure drop, and then you look at the flow rate at different positions of the plug. So I used 1 PSI at the inlet, 0 at the outlet. Now we're just looking at delta, so it doesn't matter if you're talking absolute or gauge pressure. It's the exact same thing for here. I looked at 1 millimeter open, 2, 4, 6, 8, and 10 millimeters open, and then compared that basically to CV. So now touching on mesh. I used a hex dominant automatic mesh for this, and I used a moderate fineness. So when you run the mesh, there's coarse, medium, fine, very fine, and so on. So I went with moderate, and I ended up using 4 different specific refinements to add mesh where it really matters. Now, I don't want to dive into I could talk all day about these, but I used feature refinement, which is basically it adds mesh around tight corners. So if you look at my mouse, if you look at the 90-degree angles, there's actually enhanced mesh there, and that's due to the feature refinement. Surface refinement is just adding more mesh to a surface. So I grabbed the surface basically between the housing and the plug, highlighted it, and added, increased the mesh density there. Then I did a region refinement, which just adds mesh in a certain volume, and then of course wall layers. So now you'll notice here's a zoomed in area of that slot. This is the region really where I care about and where you need a lot of mesh. So due to the refinements I used, you can count well over 10 nodes across that channel, which is actually really small. But I was able to get, the necessary mesh density in there so that my results are not going to be affected by the mesh, basically. So just a quick note on result control. There's different ways to gauge convergence. Most people, look at a convergence plot and you see residuals, and it's helpful and can definitely be indicative of how the solution is progressing, but it doesn't give you like a physical value. It doesn't say, hey, this is what my flow rate is or whatever. So ahead of time, before I run the simulation, I actually go into result control, and I am going to basically probe data at the inlet face and outlet face. So here I selected the inlet face or outlet, I'm not sure which one, but the flow rate is going to be the same. And I'm going to say, hey, every single iteration, write out what the flow rate is. So it's going to integrate over the area, integrate the velocity over the area, and give me a flow rate. And I'm going to be able to determine, when that arrives at a steady state value. So on the x-axis, it says time, but it's a steady state solution, so it really just means iterations. And then, of course, on the y is volume flow rate. So we see after about 200 iterations, the volume flow rate is converged. And this is what we really care about here. I always recommend, people may ask, what should I probe or what should I look at to judge convergence? It's always what you care about. So if in this scenario you really care about force, on the plug, well then look at force on the plug. If you care about a specific temperature on a chip on a PCB board, definitely probe that and see when it hits steady state. All right, so now I'm just going to jump out into the product. So I'm going to exit full screen. And okay, so here's the platform. And this is where I ran my simulations for the webinar. You can see I'm obviously in Google Chrome. Here's a URL. I have my 6 geometries up here and then my simulations below. So I'm going to say create a simulation. We'll go to incompressible and select OK. I'm going to name this webinar demo. I'm using the K-Omega SST turbulence model. It's a steady state. This is all good. Now the mesh is already generated because I made it for this geometry earlier, right, for one of my original simulations. Meshing can take a little bit of time, so I'm going to skip that for now. But feel free to reach out with specific meshing questions if you have any. So first I'm going to assign a material. You'll see, I should note, you'll see basically the red sections mean that they haven't been filled out. You will not be able to run a simulation until all of those are turned into green checkboxes. So we say OK, we scroll down. For water, these are all default materials that we have. You can always add your own. So if I say OK here, it's going to highlight the component because it's the only body in the platform right now in this area. But normally you would click it. I can unselect and then select it again. Now you can edit these on the fly. So if you wanted to go water, at 50 C, you could type that in, change the kinematic viscosity and density, and say OK. Next, we'll do boundary conditions. So I'm going to start with a pressure inlet. And I'm going to select that face. We're doing 1 PSI. And then we're going to do 0 at the outlet. It doesn't matter the units because it's 0. It's absolute. Again, for this type of analysis, because it's incompressible, it's not going to affect the density or anything. So gauge versus absolute doesn't really matter. So here are numerics. Now we used, we have defaults that we give the user. If you're a super advanced user and you want to change these, feel free, but I usually don't start changing these things unless I have to, right? If my simulation is diverging, if it's super unstable, then I'll come in here and change some things around, but we set you up for success here with the defaults. Now under simulation control, I'm going to run. Now it says start time and end time, but it's really just the number of iterations. This is a steady state analysis, so 1,000 is perfect for me. The right interval is just going to be every 1,000 iterations basically. I can run this on 32 cores, and we'll make a max runtime. The max runtime is to just make sure you don't burn up a bunch of core hours. The default of 3,000 is actually a little quick, so it's not even an hour. So this thing might take, 3 hours, so I'm going to bump that time up. And then, so I'm going to use result control to probe a few different things, which is super helpful. Now, we do have like a probe point, which sometimes is called a monitor point. That would just be monitoring a single point in space. And then, of course, we can look at, surface data. So let's look at, we're going to do an area. If you want an area average, that'll tell you like the mean velocity. Let's actually do an area integral, and we'll get the volume flow rate through this system. Now, the right control, we can just do every 10 iterations. It doesn't make much of a difference, but there's really not a lot of noise in this data. So that's gonna tell us the flow rate. I also think it would be worth looking at forces and moments. Now, I don't care about a moment here, but I'm curious what the force on the plug is. So I need to hide a few faces here. Awesome. So if we grab that surface, that one, so I basically grabbed, really the bottom ones are going to be what the dominant force on the plug, but I can grab basically all the faces in between. There's no reason not to, and this is going to give me a net XYZ force in newtons on the plug. The center rotation is only if you care about a torque or a moment, which I don't care about. And we'll just rename this plug forces. Awesome. So at this point, we can just hit simulation run. Oh, this is giving me a warning. So it will do it, the platform will do it on your own, but I should add a no-slip wall boundary condition to all the faces. Again, basically one of the most fundamental theories of fluids is that fluid velocity at a wall with respect to the wall was always zero, so the particle right at the wall is always sticking to the wall, and that's what creates a boundary layer. So under boundary conditions, we'll just do wall. The default is no slip, which is perfect, and then I'll just activate box selection up here, which highlights every single face, and then let's just unselect the inlet and the outlet. So now that that's all set, you can say run one live demo, and this is kicking off the simulation on a 32-core machine. Now what is really cool about this is that if you have, so I had 6 different valve positions, I can kick off all 6 simulations at once on 32 cores, leveraging a total of 192 cores, and I'll get my results back in the same amount of time as if I just ran one simulation. So on a traditional desktop solution for CFD, those would run, in series, one after the other. So you'd wait out, 6 hours. It would stop. The next one would go 6 hours, and so on. So, if each of these takes, 6 hours, you're looking at, a day and a half, basically, which really slows you down. So this guy's going. Figured I can show you the mesh a little bit. Let's jump into one where I've already run simulation. Before I jump into the post-processor, I just want to show the convergence plot. So we see over time, and this is a little rough, but we see over time the residuals are dropping, eventually, quite low, closer to 1e minus 4. We do have some turbulent oscillation, but if you look at the magnitude, the residual is so small, it's really not a big deal. Now, if we look at the area average, it should be in the UX. Let me check. Nope, UI. So here we can look at the volume flow rate. So again, the first one is at, so iteration 1. So every single iteration it was reporting volume flow rate. So you can download this chart as a JPEG if you want to drop it into a PowerPoint or something. You can also download the CSV data to do further post-processing. So when I report a volume flow rate, I usually average the last 100 iterations and use that value. So this is what the post-processor looks like. I'll go ahead and drop a cut plane in there. And let's look at velocity. Now this is, the 1 millimeter example. So the domain looks blue because the flow rate is very slow with respect to this tiny channel. Now here, you generally can't really see the elements, which is a good sign. So you want to make sure that your results are not having a huge material impact. I mean, here there's a tiny bit, but in the channel, it's not obvious. On the inlet side of this guy, the contours look smooth and good, which is a great sign. Considering that 1 millimeter gap is very, very small, I would say the mesh turned out quite well, and I can actually show it here. So the feature refinement is why this mesh right here is denser than the mesh out here. So when you do feature refinement, you specify the size of the element here, and you specify it sweeps a radius. So you can see basically from the wall out to here, it's sweeping a distance where it's adding more mesh. And you can see those are my wall layers. I have, I think, 5 of them. And now I can, I'll hide that for now. And bear with me, please. I can drop in some particle traces, which is always great for visualizing the flow. And try to map velocity. All right, just change the magnitude of the scale to get a little more coloring. Maybe. Cool. Now we can actually animate this right in the post-processor. So if you go add animations, say particle trace, hit apply. Cool. So I think I'm going to jump back into the PowerPoint. You can at least see a bit of the platform there. Let's show the force plot. Okay, so I need to figure out, just bear with me, I need to figure out, here we really care about force in the Z because that's the direction that the fluid's going to be pushing. So if we go back to this data, deselect all. So here's the pressure force in the Z. Now, it looks like it's 0. It's just because the first couple iterations have crazy numbers. So if I actually was writing out the probe data at, say, every 10 iterations, you wouldn't deal with this because, you know, by iteration, you know, 10 we're already at a much more reasonable number. So if you see out here, really the steady state value is at about 11 newtons of force in the Z direction. So again, if I were to see oscillating values here, I would be concerned. Maybe the solution isn't converged or fully set up correctly, or maybe it's just oscillatory in nature. Anyway, I really like using that result control. So let's jump back in. So I grabbed some good looking pictures to kind of you know, post-process ahead of time so we can take a look at some of those. Here are just some particle traces showing velocity, and yeah, fairly interesting. And I guess, you know, I will note it is important to have, you know, outlet extension a little bit because you see these particle tracers are going a bunch of different directions. You don't want a lot of swirl over your outlet pressure boundary condition because you'll run into mass balance problems, and then your solution won't be numerically stable and it'll diverge. So if nothing else, just add enough that you can let the flow straighten out. So here's just velocity through those channels. It's not surprising to see that, you know, the highest velocity obviously is through the gap between the plug and the housing. I did find it kind of interesting on the left that the magnitude doesn't jet out parallel to the plug edge there. It kind of goes straight up when I would expect it to go farther to the left side or over here. And then over here is a more expected trajectory, basically. All right, so here's pressure, and you know, you can set I think I scaled it just to get something that kind of zeroed in. So all you have to do is just, you know, double click and reset the magnitude. If there's one node that has a super high or super low pressure, it can kind of distort the results. But yeah, you know, 6,000, whatever, 800 pascals, that's right about an inch of water, just like our boundary condition. And then you see 0 on the outlet side. It is interesting to see, you know, you get local low pressures in certain areas. If you see my mouth, it's a little hard to see, but there's green right in that small jetting area where the high velocity is. Of course, kind of follows Bernoulli's principle. You would expect a low pressure where you have a super high velocity. So these are the charts I developed, and again, I'm basically post-processing using that result control data. So this is average data, so it's very accurate. Percent open on the x-axis and flow coefficient on the y. This looks, you know, fairly linear. So it's not incredibly surprising, but different geometry can have adverse effects on the flow coefficient curve. So it's interesting to check out. Now, flow rate versus distance open. This curve is actually not too interesting because, as I mentioned before, basically the equation for flow coefficient reduces once your specific gravity is 1 and your pressure delta is set to 1. It's really just you know, flow rate versus distance open kind of thing. It's the exact same. But if you want to model it at different pressure deltas, you know, that's when these curves can get a little more interesting. And regardless, they are helpful. So lastly, probably the coolest part of this analysis, I did plug position versus force on the plug. So this is grabbing all the forces for every face. So on the back side, if there was a low pressure that basically was a pull in the end, that was included. And my peak is, around 75 newtons. And interestingly enough, it's almost like a bit of a paradox where you don't understand exactly where the highest force is going to be. You have the most volume flow going through at the highest open position, but there's not really high pressure gradients. So 2 millimeters was the most for me. Interestingly enough, 1 millimeter open really had no force, which was quite surprising. So I couldn't really have predicted ahead of time what this would have looked like. It's certainly not linear, and I was able to extract a lot of helpful information here. So finally, if you have any questions, please jump into the chat and send them my way. That's all I have to show you guys today, but I hope you found it useful, and I'd be happy to answer any follow-up questions with my setup, or dive into the platform if someone will find that valuable as well. So I'm going to wait a few minutes here for questions, and I'll answer them as they come in. So someone is asking, does the software have considerations for choked flow conditions? I'm not exactly positive what you mean there. I would say yes. It might come down to a geometry change. So not positive, but I would say, in general, if you're trying to capture, Venturi effect or something similar, platform certainly is able to do that. Okay, so so predict or identify cavitation. So generally how we go about cavitation is we calculate as a custom result quantity the cavitation number. We don't explicitly model it because it can be tough, but if you basically use an iso volume and look at a certain cavitation number and see which is just an equation that it's like a pressure delta, and I think there's a velocity term that can be calculated easily. You can kind of understand where cavitation might occur. So that's how we would approach that. Awesome. I think that's it. Thank you very much, everyone. And please attend our next webinar. If you have any questions, you can reach out on support@simscale.com. Or if you just go to simscale.com and start a message in the lower right-hand corner, we have a messaging system. Someone will pick that up and we can help you out. So feel free to reach out, and thank you for attending today.